Okay, so hello everybody. Welcome to this new MAX webinar. The topic is managing, simplifying, and disseminating high-throughput computational material science with AiiDA, AiiDAlab, and the Materials Cloud Archive. My name is Giovanni Pizzi. I will be the moderator of today's webinar. I'm from EPFL in Switzerland, and I'm going to introduce to you also the speakers of today in a moment. Let me remind you, this is a second of a series of webinars held by the MAX Center of Excellence on the topic of the most recent developments on the MAX flagship codes, and in general on all the work which is being done toward reaching exascale simulation capabilities, especially for material science. The first one was on Quantum Espresso code and its capabilities, and you can find the video of the last recording of the last webinar already online on the MAX website. So you have the link here. And I also remind you there will be a number of other webinars in the upcoming weeks. The next one, which are already scheduled, are on the Yambo code and on the CP2K code, and you will find exact dates on the website, and there will be more to follow. Let me just remind you what is one of the key focuses in MAX, which is exactly the title of this webinar series and this webinar of today, which is exactly managing, simplifying, and disseminating high-throughput computational material science. And in particular, one of the deliverables in MAX is really to push for the convergence of three key aspects in material science research and simulations, which are high-performance computing, or HPC, high-throughput computing, or HTC, and high-performance data analytics, or HPDA. And these three really have a specific work package in MAX, which is focused on making them converge and integrating the tools. And the ultimate goal is really to push for open science, push for reproducible science and reproducibility, and make sure that the data you produce in your research can be shared according to the FAIR principles of research data. In MAX, we've been developing a number of tools to make all of this possible. In particular, the two tools of choice, which we also be presented today, are on one side AiiDA, and on the other side the Materials Cloud. AiiDA is really, we can call it an operating system. It's really a Python infrastructure which allows you to manage all your simulations, to guarantee reproducibility of your research, to track the provenance of your simulations, so the history of how your data was produced, automated all your simulations in a high throughput fashion, even when you have to manage tens of thousands of simulations concurrently. On the other hand, Materials Cloud is a web portal. You have the links here for both projects, which is really focused on fair data disseminations and on making it available both curated with the properties, but also the raw data with the provenances tracked by AiiDA. The online tools to predict new properties provide cloud computing through AiiDA, and also provide educational material like videos and tutorials. You will first hear in the first of the three talks today, introduction on AiiDA itself, and also actually on its use and combination with Quantum Espresso, in particular the GPU-enabled Quantum Espresso version with Sirius code. The talk will be by Dr. Sebastian Huber in a couple of minutes. Then, for what concerns the Materials Cloud, we won't have the time to discuss all sections and all components, but we'll hear two parts. First, there will be a talk by Dr. Alexander Yakutovich on AiiDAlab, which is our cloud simulation platform, which leverages AiiDA to provide powerful GUIs. And the third talk, we'll hear about the Materials Cloud Archive, which is our platform to provide long-term storage of research data and provide DOIs to them to make them findable. And this will be given by Dr. Valeria Garnata. Actually, I'm very proud to announce that actually today, with this webinar, we are unveiling the new archive. It's a completely new redesigned engine, which is based on the Invenio infrastructure, which is the same infrastructure which is used by Zenodo. If you know, it's a massive repository managed by CERN, which contains millions of data entries. You will hear about all this in Valeria's talk. But we are not just, MAX is not closed into itself, it's really part of a much broader worldwide community. In particular, we are part of the Optimate Consortium, which includes about 10 other major crystal structure databases, with the goal of really providing standard APIs to allow to run the same query and fetch any crystal structure from very different databases, with the same language, the same query syntax for all of them. You can find information here. AiiDA and the Materials Cloud both provide already a server that can serve data through this API, And here I'm just going to show very briefly a 30-second video where you see a client which has been developed by us, in particular by Dr. Kasper Andersen in our team, where you can essentially go and search for any structure in any of the databases supported by having a very nice user interface where you can visualize the structure, you can look at the crystal structure sites and the chemical position, the chemical sites, unit cell, and you can easily select and filter with advanced filters the structure you want to look at. Like you want to include molybdenum in this case, you can choose how many elements you want to have, you can exclude specific elements like we are going to do now by double clicking on C and making it red. Just before we start, I want to also acknowledge all the other projects beside Max, which also are sponsoring the development of AiiDA and Materials Cloud. And now let me go and move in presenting the speakers. I just want to mention one final thing, that during the presentation, there will be some instant polls and you'll be able to participate by replying directly in the box that will pop up. And also you should have on the bottom, you should see one now, and you will have at the bottom a Q&A button where you can already type in your questions. We'll try to answer live. After each talk, we'll read one of the questions and let the speaker answer live. With this, I'll stop my sharing and I'll introduce the first speaker of today, which is Dr. Sebastian Huber. He received his master's degree in chemistry and physics from the University of Utrecht in 2011, and then his PhD degree from the University of Twente in 2016 in computational material science. Since then, he has joined the theory and simulation group at the PFL as a postdoctoral researcher, and is working on the AIDA materials, AIDA informatics platform, for which he's one of the lead developers. Please, Sebastian, the floor is now yours.
Thank you very much, Giovanni. Can everybody hear me and see my screen?
Yes.
Okay, very good. Thank you. So as Giovanni already alluded to, in this talk, in the next 15 minutes, I will talk to you about the challenges that we face in modern computational science, and specifically how we can manage high throughput computational science. I'll first introduce the problem and then present the AIDA informatics platform infrastructure that we've been developing at EPFL under the scope of the MAX project to tackle the challenges posed by this field. And secondly, I will give an actual example of an application that we've used AIDA ourselves for, in combination with the SIRIUS library and Quantum Espresso. So the reason that we're all here is because over the last few decades, we've seen an enormous increase in computational power that's been available. So you see on the left an image from the top 500 organization that monitors the available computational time. And you see on the left, you see the performance that is available as a function of the years. And we see here in orange the #1 top supercomputer. And in green, it's the sum of all the available computational power. And we see an enormous increase. And essentially what this means is that a calculation that took months in 1995 currently only takes seconds. And likewise, where scientific studies could realistically only address a single material in 1995, now we run typically tens of thousands in high throughput studies. So with this newfound power, we also have a lot of extra challenges. And so one is the workflow automation. As I said, nowadays modern computational studies no longer just perform single isolated calculations, but are often a complex sequence of calculations that have complex interconnections with potential failure cases that need to be dealt with. And so what we need is a tool that allows us to implement these and define these complex workflows and implement complex error handling. And we need an engine that scales to high throughput modes and allows to automatically run these workflows. Running these many workflows will produce a lot of data, and likewise, its data needs to be managed. And most importantly, it should be stored reliably and efficiently. But nonetheless, at the same time, this data should also be queryable and interoperable. This way, it makes it possible for this data to be reused in subsequent studies. And one key aspect that we in AIDA focus a lot on is reproducibility. One of the cornerstones of the scientific method is reproducibility. The more often we can reproduce a certain theory or a result, the more we have confidence in its predictions. And when it comes to data, reproducibility is provided by storing the full provenance. And so when we talk about provenance, we can give a very simple recipe of what we mean when we speak about provenance. Think of any data transformation or a calculation as imaged here by this schematic red square. It's important to store all of these calculations, but not just the calculation itself, also the inputs that were actually consumed by it, so the data that was transformed, and the outputs that are produced. But most crucially, we should store the explicit links between them. Now, in this trivial example, this might seem trivial to store these links. That might not seem that important. But if we look at more complex problems, it clearly quickly becomes apparent that this is very, very important indeed. Moreover, there's a requirement. The storage of data provenance needs to be automated, and it needs to be stored as the data is created. The reason why is illustrated by this image on the bottom right, which is a schematic representation of a database where each point that you see corresponds to a piece of data or a data transformation, a calculation, if you will, and they are connected by the lines indicating whether they're inputs or outputs. And this is just a very modest research project, and you can already see the enormous complexity that is captured within. And so it's my conviction that restoring this information a posteriori, after the fact, is practically impossible. It might technically be possible, but practically it will be too time consuming and will almost be guaranteed to be incomplete and faulty. So what we need is a tool that does this automatically for us. And this brings me to AiiDA, which is the tool that we've been developing within the scope of the Max project at EPFL, but with a lot of collaborators outside of EPFL as well. That is a computational infrastructure that provides a scalable workflow engine that has automated full data provenance, comes with built-in support for high-performance computing and their infrastructures, and a flexible plugin system. As you'll see later, AiiDA is completely domain agnostic. That is to say, it is not built to work with any particular simulation software, but can be extended to work with any. A few small details. It's implemented in Python, and also the API is written in Python, although there's a command line client and the REST API. It's MIT licensed, so it's open source, and the source is maintained at GitHub, and so can be freely contributed to and used. To get started quickly, I will give you a quick example. We're here in a Max meeting, and one of the Max codes is Quantum Espresso. And to give you an idea of how you can run an HPC code through Quantum Espresso, here's a quick example. And essentially, all we have to do in AiiDA is we define the inputs in Python. So this is Python syntax, and we define a dictionary with the required inputs. So we define the code that we want to use, which is QE that I've installed on my local host machine. Some structure. There's various ways of constructing these. One way is to load from CIF, as I've done here, from a CIF file. We define the K-points, a 2x2x2 mesh, some parameters, just a simple SCF with some standard cutoffs, and I define some metadata options, for example, the number of machines that I want to use in the maximum wall clock seconds. Finally, I just submit this PW calculation with these inputs, and this submits it to the daemon, and the daemon will take over and take care of everything. It will make sure of creating all the input files, sending it to the machine where it needs to be run. It will submit it to the scheduler. It will pull the scheduler for the job, whether to see it's finished. Once it's finished, it will retrieve all the output files, parse them, and store everything in a database. And there's nothing that the user has to do. Now, what does this look like for the user's perspective? This is a screenshot of the command line interface of AiiDA, where I ask, show me all the calculations that have recently run. And you can see here indeed that it ran the PW calculation, and it's currently finished with an exit status of 0. So everything was okay. As you will notice that this only remarks the calculation, so the data transformation itself. But as promised, AiiDA does not only store the calculation, but the entire provenance. So here you will see all the input on the top. You will see all the input nodes, the code, the structure data, the UPF data that was used, the K-points data, and the input dictionary that were defined on the left. But not only the inputs, also the outputs that have been produced. So we see a bands data containing the band structure and a dictionary with some output parameters. On top of this, submitting to a different computer is now as simple as changing a single line. Before, in the first example, I submitted to localhost. Let's say I've now installed QE on Pitstained, which is a high-performance computer at the Swiss National Computational Center in Lugano. And I've configured it through AiiDA. I can just swap the single line and submit it again. And AiiDA will now take care of submitting everything over an SSH connection and actually interacting with a Slurm cluster without you having to change anything. All this complexity is abstracted by AiiDA, making it very simple to use multiple computational infrastructures with a single tool. This was just a single calculation, but as I alluded to in the initial introduction, we rarely ever execute single calculations, although it occurs now and again, but often we actually execute complex workflows. And AiiDA comes with a very powerful workflow language. Now, I have to stress again that AiiDA is domain agnostic, so it doesn't actually provide concrete workflow implementations, but these are instead provided by the plugins. So the Quantum Espresso plugin provides the PW base workchain, which is a simple workflow that wraps around the PW executable and adds a lot of functionality over the normal calculation. For example, you see here that instead of specifying explicit k-points mesh, I just provide a distance. If we now execute it, we can also see that the base workchain consists of multiple steps. We see here the record of the base workchain itself. And in the first step, it will create k-points from distance function that from this distance will create the mesh that is appropriate for the given structure. And then we see that it launches consecutively 2 calculations. This is, again, also captured in the provenance graph. With a single command, you can have AiiDA plot this PDF, and you can see that the entire provenance is captured. So we see all the inputs that have been passed into the PW base workchain. It calls first the create k-points from distance and produced the k-points mesh that is appropriate for this structure. So it was 555 was to be determined, and then the 2 calculations were launched. The reasons that there were 2 calculations instead of 1 is because the base workchain checked at the end of the first one that the occupied bands and realized that there were too few bands. So it relaunched a second time the calculation after having increased the number of bands. This is just one of the many handlers that are implemented for this workflow. There's other handlers for dealing with when the calculation runs out of wall time, when there's a problem with convergence, etc. Again, this is up to the plugin itself and depends on each workflow. Then I want to go to the next section of this presentation, which is about SIRIUS. And SIRIUS is a library for plane wave electronic structure codes that is being developed by people listed here at CSCS and in collaboration with ETH Zurich. And the motivation for this library is essentially the following. On the left, we see a small schematic of how things used to be developed in the last few decades. We have domain scientists developing scientific code, and which is then executed on classical HPC platforms. What SIRIUS tries to do is to separate these constraints and these requirements to have domain scientists just focus on the scientific code, and then have computational scientists, experts work on domain-specific libraries, really having to focus on the numerics, on efficiency, on performance, and making sure that this can run on any number of architectures. So SIRIUS fits here in this domain-specific libraries. And if you look on the right, how this fits in with the existing scientific codes, we have SIRIUS is currently interfaced with QE, CP2K, IPI, and Exciting. And what SIRIUS tries to do is to take away all the heavy numerics that all these codes have to do, for example, computing the DFT ground state, and take it away as a burden from those codes. And it just returns the DFT ground state, and then the scientific codes can focus on doing the physics, so computing the forces, computing the stresses, etc. They no longer have to worry about all the complexity underneath. So we've been collaborating with the authors of SIRIUS, and the first step was to, because we want to use this in production for our material discovery projects, the first step was to benchmark it. And so we've created a benchmark set of 550 crystal structures with a wide range of chemical and geometrical properties. And we use our AiiDA Quantum Espresso plugin to run the base workchain, the workflow with error handling capacity that I've presented before, to run for each of these, for each code that we're interested in, all these structures, a simple SCF calculation. And then we compare the results in terms of efficiency and the actual numbers, the precision. For this, we use a useful tool in AiiDA called groups, which you can think of as folders. And so on the file system, and the nodes that you put in them are the files. So you can structure your nodes. And so here I have a group called structures benchmark, which you can see contains 550 nodes, which corresponds to those 550 structures. And I've now run normal PW version 6.4 and the one enabled with SIRIUS 652 for all these 550 structures. This is again all automated by AiiDA, and it's very easy to run. And as we have seen, all of this is stored automatically in a database. I've also mentioned in the introduction that it's important for the data to be queryable. And here I show the tool called Query Build in AiiDA that allows you to query your database. I won't go into the details, but to give you a taste of what this looks like, you can construct a Query Builder instance, and we're going to use it to retrieve all the computed total energies for PW64. So I append the group, and I'm looking for the group with this label. I'm looking for all the calculations that are stored in this group. And finally, I'm really interested in the output dictionary produced by that calculation, and specifically the total energy attribute. And just by calling builder.flat, it will give me a list of all the total energies that were produced by these calculations. I can do the same for Sirius, and I can compare these numbers, and because it's all in Python, I can typically use like NumPy, Pandas, and Matplotlib to compare these numbers. This is what I've done here. So here you see a histogram of these two versions, so normal quantum espresso and Sirius-enabled quantum espresso, where I compare for these 555 calculations the total energy on the left and the difference between them, the total force difference, and the total difference in the stress. And as you can see, these numbers are negligible differences compared to the accuracy that we would typically require for scientific publications and for real studies. So that's very good. The remaining discrepancies are just due to the differences generated by the different numerical algorithms and platforms, where the normal QE is run on CPUs, and for example, with QE-SIRIUS is all run on GPUs. And because QE-SIRIUS allows us to run on GPUs, we can see here also a histogram of the time that was required, the wall time for normal QE versus Sirius. And we see that on average, we get a speed up of a factor of 6 when using Sirius. Finally, a small note on high throughput. These were just these benchmark sets just run 550 calculations, which we can call high throughput, but for our study that we're running now, we need to run tens of thousands of structures. And so we needed really an engine to be high throughput. And as of AiiDA 1.0, which is the culmination of years of work to make it more high throughput capable, we have released this in October last year, and it's become a lot more responsive compared to the first few releases by changing from a polling-based to event-based design. And it's also become a lot more scalable. If you have a powerful server to run this on, you can run this on your normal laptop, but the more powerful your machine becomes, the more you can arbitrarily demand more daemon workers, and they can chew through more workflows in parallel. We've already tested this, and we can easily achieve numbers of tens of thousands of processes per hour. Typically, this is more than enough to fill your cluster scheduler. As you can see here on the right, this is a plot of the resources that I've used for our project on PitStained. And we have about 200,000 node hours for a semester, or for one period. And you can see that with AiiDA, and these are all single node jobs, it was very easy to fill the full the cluster scheduler queue and to fully use our allocation. On top of this, we've made sure not to overload the clusters, even in high throughput modes, by building in sophisticated mechanisms that will automatically deal with connection loss. So since AiiDA is running remotely over SSH, it won't, the calculations won't crash. It will automatically deal with this when the connection comes back online, and also will bundle requests as to not overload the server and the scheduler itself. So to conclude, I've presented AiiDA, which is a computational infrastructure that allows high throughput automated calculations on normal computational or HPC infrastructure. I want to remind you can also use it to run QE on your workstation or even your laptop. It provides reproducible and robust workflows with automated error handling. All the workflows that are run are automatically tracked in a database, as well as all the data that is produced. So the full provenance is stored, and all this data is queryable, which allows directly to perform high performance data analytics. And the second part, I've presented Sirius, which is a domain-specific library for plane wave electronic structure codes. I've shown specifically the usage with Quantum Espresso, but it has been interfaced with different quantum engines. And the current status is that the differences between normal QE and QE-SIRIUS are negligibly small for the total energies, forces, and stresses. And so we're using it in production now. And by allowing to run it on GPUs, we have an average speed up factor of 6. So with this, I would like to thank you for your attention, and the MAX European Center of Excellence for their support of this project. Of course, EPFL, Marvel, another project that supports this, and the Platform for Advanced Scientific Computing. On top of that, of course, all the authors and the contributors that have made AiiDA a possibility, both within EPFL and the MAX project, but we also have a lot of contributors outside all over the world So big thank you to them. And with that, I would like to thank you. Thank you very much.
Thank you very much, Sebastian. And we are trying to reply to the questions live in the Q&A box, so feel free to continue asking. I will not take questions now in order to stay on time. And we'll just start, we'll go on and introduce the next speaker today, which is Dr. Alexander Ekutovic. Alexander received his master's degree in chemistry jointly from the Moscow State University and from Chimie Tech in 2013. And in 2018, he received a PhD in chemistry for the research done at EMPA in Switzerland. Since then, Alexander joined both the LSMO and the THEOS groups as a postdoc at TFL, where he's now leading the development of the AiiDAlab platform that he's now going to introduce to us. Please, Sasha, the floor is yours.
Right. Yeah, thanks a lot, Giovanni, for the kind introduction. Can you hear me well? Just
yes. Okay,
great. So, all right. So, as Sebastian already introduced, we have this powerful AiiDA with a lot of capabilities, and in addition, we have the capability to run turnkey workflows that allow us to manage or to simulate complex processes. What we realized quite quickly after this possibility, after we have this possibility, we can transfer it to somebody who is not that experienced with simulations. So we can actually give this capability to run simulation to the experimentalists who can run the simulation and also analyze the results. That's why that was the original idea why we wanted to introduce AiiDAlab. And with this, I would like to let's say take a step back and to discuss a little bit where we stand now. So the simulation science has made a great progress in the last 30 years. And as you can see on the slide, in 2013, there was a chemistry prize given to the computational scientists. And if you read in the press release, you'll find such a sentence. Simulations are so realistic that they predict the outcome of traditional experiments. And this is something that wouldn't be possible, let's say, 30 years ago. And again, if you look at the press release, computational scientists are discussing that if they would come to the experimentalists and show their results, and the results wouldn't match, actually the first person to blame would be the computational scientists. And since the situation has changed now, and computationals are considered as the let's say another experiment, they can be used in parallel with the traditional experiments. And this is why I would like you also to have a look a little bit from the top perspective, how the modern science look like. So we have three pillars. One pillar is the experiment, and obviously the experiment is mostly done by experimental scientists. Also, we have the second traditional pillar is the theory, which is mostly done by theoretical and computational scientists. However, as I already introduced in the previous slide, now we have a rise of the third pillar, which is the simulation. And to date, the simulations are mostly done by computational scientists. However, we would like to kind of challenge the status quo and to perceive simulations as a merging point between theory and experiment. And if you think about it, it makes a lot of sense because the experimentalists are the ones who would like to use our simulation results and to compare it to their outcome. While we as a computational scientists, we can develop our computational models and provide them to the experimentalists for the comparison. And that's why I would like to kind of introduce this motivation through the question. So, as you know, science is evolving as a collaboration between theory and experiment. However, the means of communication between the two parts are rather inefficient. So think about it. If as experimentalists, basically, if experimentalists are the ones who can verify theoretical models against the measured data, are they aware of the simulation tools that we are developing? And the second question is, if you would like to communicate the results of your simulations to the experimental colleague, how would you do it? Would you spend a lot of time preparing a PDF report and send it via email, or prepare a presentation, or would you like to use something more advanced? And with this, I mean, if you would like to prepare it yourself, how much time would you spend converting your data in different data formats, or let's say make your output data look nice and understandable by the non-experts in the simulations? And again, how much time would it take? And the last thing, would you like to be able to instruct your experimental collaborator to run calculations basically in the browser? And based on these ideas, we kind of built AiiDAlab. We know already that AiiDA by itself is quite a powerful tool. It allows us to run complex workflows. It stores all this, the data and the data provenance on the computer where AiiDA is installed, but it has Python or command line interface. And it's not a secret that not everybody in the scientific community is familiar with Python and command line. Most of scientists would like to use this tool and to run the simulations, but none of them have the expertise to do that. And since we are developing the workflows, and it is quite natural to provide access to these workflows to the non-computationalists, we decided to introduce AiiDAlab, which is fully integrated with AiiDA. And since then, it also has all the capabilities and all the nice features of AiiDA, but also it provides a user-friendly web interface with Jupyter and Jupyter notebooks and widgets. It allows for easy application development. You don't need to do any web development. You actually can write all the code in Python, directly in Python. And it also provides the collaborative environment for you to collaborate. For example, if you're an experimentalist, you would like to cooperate with somebody who is doing the simulations, you can do it through AiiDAlab. And also it comes with the handy set of visualization and editing tools. And last but not least, if you happen to have a nice tool that, let's say you would like to publish, you can wrap it up in an AiiDAlab application, put it in our application store, and then the application will be available for all the users from all the AiiDAlab users. Okay, so now, and with this, I would like to introduce AiiDAlab interface. So as you can see on the top, this is the home. So on the left side of the screen, you see this homepage of AiiDAlab. And it is the top part of the homepage is visually different from the others. This is so-called home application. It cannot be uninstalled because this is the core application of AiiDAlab. It provides the basic functionalities like a file manager to upload things, to upload data on AiiDAlab, and also to download it from there. It has a standard Linux terminal if you want to use it. It has the task manager. It has the App Store, the one that I mentioned before, and it also has the help button that allows you to, that gives you to some documentation. Explaining how to use AiiDAlab and how to, for example, build your own application. And also you have these 4 rectangles that are basically the applications. You can change their order, or you can also install and uninstall them if you want to. What is also important that we not only provide the way to install application, but AiiDAlab is taking care of managing the updates. So if you would like to update your application, there will be, first of all, a yellow text saying that update is available. If you click on Manage App, then you will be able to click on Update button, and the application will be brought to the newest state. Application development is quite easy. Basically, what you need to do is to provide a set of Jupyter notebooks, and also all this should be in the on the Git repository. And then in order to make this application available on AiiDAlab, you need to make a PR, pull request to AiiDAlab registry. And once it is accepted, your application will appear in the list. So with this, I would like to give you a quick example how one can run simulations using AiiDAlab. So this is a quick video where we'll be first submitting the geometry optimization using AiiDAlab. And I'll take the structure from computer. So you have different possibilities where you can take structure. I'll take from my local computer. I'll select the file, and then you see that the file appears on the screen. But you can notice that the structure is not perfect. So first of all, it has a solvent molecule, the methane. So what we need to do first is to find those solvent molecules. And we have these nice editing tools that allows you to find it. And then we can delete the solvent molecule. The next step is to understand whether the structure is, let's say, doesn't have atomic overlaps. And again, we have the tool for that. And so what we do, we deselect the atom that we need, and we delete the atom that is overlapping. Once this is done, we will store the structure, provide some description, and then we will select the calls where we would like to launch our simulation. So it will be CPTK on FIDIS and DDC on FIDIS. So DDC is the code that will assign atomic charges, point charges to every atom. So now the simulation is submitted, and we can eventually close the page. So what we'll do next, we'll go to the isotherm computations. We will select the structures that were optimized previously. So I will not wait until this, obviously we cannot wait until the previous simulation is done. So we'll just select the ones that are already in the database. Then I'll take the structure. I will select the guest molecules that I would like to put in the framework. So again, I'm computing isotherm here. So I'll be changing the pressure, and my end result is how many molecules can be loaded in the framework depending on the different pressures. So I'll define the range of pressures I'm working with. So it will be from 5 bar to 65 bar. And then I'll select 2 codes. First will be C++ to compute the geometric properties, and second will be Raspa to compute the isotherm. All right, so again, the results are submitted, and we can also close the page. And the last thing I'm going to show here is how we can actually browse the results of this the simulation. So I'll select this the guest molecule. I will click on plot, and here you will have the list of like the structures that the simulation, the results that were computed. So you have the initial structure, you have the isotherm itself. So again, you see that the pressure, the CO2 loading depending on the pressure. What you can also do, you can compare your results to the experimental data. So you can just put them in the window below, and you can click on plot, and then the results will be superimposed. And if you want, you can also look at a more detailed report and download it, and you import it into your into Excel program. All right, so this was about how one can use and how one can submit simulations using AiiDAlab. And the next thing I'm going to talk about is how introduction of AiiDAlab has changed a life basically of one laboratory. So before AiiDAlab, just a quick kind of pre-story. So the laboratory is mostly working on synthesizing the graphene nanoribbons and measuring the electronic properties of those. So before AiiDAlab was introduced to this laboratory, the experimental collaborators would ask computationalists, some while ago we discussed ribbons A, B, and C. Did you compute the band structure of those? And even if we did, we typically don't know, because it could happen so much time, so long ago, so that we even don't remember. And the obvious answer, I can recompute it. So I can, and the second question would be, how much time would it take to have the band structure of those? And I mean, this will probably take 2 or 3 days until the results are there. So with the introduction of AiiDAlab, things has changed dramatically. This is the email from the head of the laboratory, who actually writes directly to the experimental PhD student and puts the computational person in CC, Carlo Pinedoli. And he says, we have the band structures for the last 2 nanoribbons. So he is already aware what what simulations were already done, and he is aware of the results of those simulations. And he is explicitly expecting that the computing the 3rd one wouldn't take a lot of time. And here you see the answer from the experimental PhD student. He says, I will run AIDA deep calculation on the ribbon to check the band structure of it. So as you can see, no support is needed. And this is great, because those simulations that I'm shown here, so the band structure calculation, kind of becoming the standard simulation that the laboratory is doing. And there is not much science involved into repeating the same simulation over and over. So it makes total sense to automate them, and also provide this automated workflow to the experimentalists, so that they can go to the AiiDAlab, upload the structure of graphene nanoribbon, and compute the band structure for those. And then, since the interface is can be adapted at the need of the person who is actually looking at it. I will show you now how the browsing the results of this database looks like. So I'll just select the search database of non-ribbon. Then I'll click on search, and here you see the table of available non-ribbons that are already computed. So you can click on show, and here you have a more detailed report about what are the computed results of this specific non-ribbon. You can so this all is interactive. You can look at your orbitals. You can also change the band, and then the view will be adapted accordingly. You can also show the spin density. And again, this is all quite modular, and you can adapt those tools for your needs. And all of this is written in Python, so not much of web development is needed. And the second tool is, I'm showing here, is the PDOS. You can imagine how much time would it take to prepare a PDOS plot if you do it like in a standard conventional way. However, since AiiDAlab has access to all the data that were stored by AiiDA, you can just click on the atoms, take the structure, click on the atoms on which you want to project your density of states. You click on plot, and the results are here. So it really simplifies a lot the workflow. Okay, so this is already the end of my presentation. I hope I could convince you that AiiDAlab provides an environment where people with different expertise can collaborate on a common computational project. It allows to save a lot of time and allows to avoid mistakes, because you don't need to do things like converting data from one format to another. You don't need to do a lot of coding in order to present your results in a nice way. This is already in code in AiiDAlab. It can be reused by others. And also, thanks to the modularity of AiiDAlab, those applications can be built quite easily by just combining little tools that we provide with AiiDAlab widget base. So we have a set of little widgets that you can incorporate, and you can build your AiiDAlab application based on those tools. And then you can share this tool with the whole world. And with this, I would like to thank you all for your attention, and yeah, I'm ready for questions.
Thank you very much, Sasha. Again, in terms of timing, I prefer to keep the question at the end. We've been answering them live. Feel free to ask more, and we have the time to answer a few live later. I'll now continue with the third speaker of today, which is Dr. Valeria Granata. Valeria graduated in physics at the University of Naples Federico II in Italy, and then she moved to Geneva to work at CERN as a PhD student and then as a fellow scientist. She received her PhD from Brunel University London in 2004, and then worked as a postdoctoral researcher at the Laboratoire d'Annecy de Physique des Particules in France. Valeria moved to PFL in 2009, and since 2019, she joined the THEOS group, the Theory and Simulation group, to work on the development and as the lead software developer of the Material-Scale archive. As I said before, is being released today, and she's going to introduce now. Thank you, Valeria. The floor is yours.
Thank you, Giovanni, for the presentation. This is indeed the MAX webinar on depositing data on the Materials Cloud archive. The Materials Cloud is a web platform, and the archive is one of the 5 sections of Materials Cloud. Indeed, the Materials Cloud is composed of a section Learn, Work, Discover, Explore, and the archive itself is conceived to enable open and seamless sharing of resources for computational science. And it has as main goals to support researchers in their scientific projects, to make research fair and reproducible, and to guarantee a long-term storage of raw and curated data, particularly focusing on the full provenance of calculations. The Materials Cloud Archive is a moderated repository for computational material science. It guarantees long-term storage of records and associated metadata for at least 10 years. It runs on virtual machines in the OpenStack installation at the Swiss National Supercomputing Center, and all the data and metadata are stored in the object store of the CSCS. Each record that is on the archive, to each record is associated a DOI, a persistent identifier. Here is an example of a DOI. The DOI released by the ETHZ library, and so this will make them very easily accessible. We also, in the application, developed some standard protocols allowing people to easily, other applications to easily harvest the records in the archive through OAI PMH protocols or JSON REST APIs. To upload a record on the Materials Cloud archive, there are some criteria that needs to be satisfied. In particularly, the content has to be relevant computational material science data. The quality of the data should be of a level of a journal. You don't need to have a paper associated to your data, but the quality of the data provided should be of the same level. One can see the archive as an equivalent of a preprint server for a paper. So there is a moderation behind it, and records are reviewed by our moderators. We do accept experimental work, but in specific cases when the authors are affiliated with the Materials Cloud partners, or in the case the work, the experimental work somehow validate or disprove some computational results. So in these two cases, we do accept the experimental, to publish the experimental work. The file you can upload together with your record should be a maximum 5 gigabytes. If you are working with AIiDA and you would like to upload an AIiDA database, so the limit goes to 50 gigabytes. We do accept larger data sets. So in case you would like to upload more than these limits, you will have just to ask us. So send your request and we will evaluate it. Of course, between the files, there should not be the paper itself or any supplementary materials, and you should have the legal right to publish the content you have uploaded on the archive. We do accept several licenses. As Giovanni said in the introduction, we are today at the second release of the Materials Cloud Archive. The first release was in March 2017. It was an application built with the technologies Flask, Jinja, SQL, Alchemy. Today we are at the second release, and it's actually not an upgrade or an update of the previous one, but it's a completely new application built within the Invenio framework, developed at CERN. Invenio is a framework behind Zenodo. Many of you might probably know it. It's a repository that hosts today more than 2 million records. The Invenio framework is quite a large framework and packed of technologies. Some of them are listed here. When we started developing the application, the new application, Materials Cloud Archive in the Invenio framework, we soon realized we needed to anyway develop some features by ourselves because they didn't come by default in the framework. This is in particular related to the fact that the archive is a moderated repository, things that, for example, Zenodo is not. Overall, we try to address all the needs of the users, the moderators, and the administrators. For a user here, I mean anybody who would like to upload a record on the archive. A moderator is a person who is in charge of reviewing the records submitted, and the administrator has some specific tasks. So we improved the application for the user, simplifying as much as possible the submission procedure. Also making easier the edition of published records. It's easier to change references and keywords after the record has been published. It's easy to create a new version of a record. The DOI is registered in the moment the record is created in the archive, so even if it's just in a status of draft. Of course, the DOI will be released only when the record is then finally published on the archive. The user can access a personal work area where he or she has access to the records uploaded, and there is a search engine behind the Invenio framework that allows to easily search for keywords or free text. Overall, in the application, we try to inform the user of the status of the record throughout the entire moderation process. So from the moment the record is created to when the record is finally published, the user is constantly informed of what's happening during the moderation process. And this is done with the email exchange by the application and also with the messages directly printed on the application. For the moderators, we simplify some of the tasks that is in charge, like reviewing the record, approving it for publication, or in case a record has to be rejected. But these are really exceptional cases. For the administrator, retracting a record or adding, for example, links to the Explore and Discover sections. Indeed, if you upload your record, your data on the Materials Cloud archive, this data can be then used in other sections of Materials Cloud. As I said, there are 5 sections. This is an example of a record that has been published on the archive, and it has 2 links to the section Explore and Discover. This is an example indeed of how it looks, these links, the Discover and Explore sections. So in the Discover section, you can easily browse your data with interactive plots. In the Explore section, if your work is on AiiDA, the database is completely completely in the application, and anybody could download it if needed. I'm going to show you now quickly a video that will show the main features and functionality of the application as listed here. So the URL is as shown on top, archive.materialscloud.org. On the front page, you see the list of records that have been published with the DOI well displayed. You can click on any of the records to see the content, the description, the title, the links I was just mentioning, and a list of files associated. There are also links to external references and previous version to previous links to previous versions, sorry. To sign up in the application, there is a sign up button. If you are a new user, you enter your email and a password of your choice. You click on sign up. This will send to your email address an email to confirm your email. You will need indeed to click to confirm your account. At this moment, you have now access to your own workspace, clicking on the button My Records. You can also change information on your profile, or for example, change your password. So clicking on My Records, here you will see the records that you uploaded on the archive, divided in these 3 sections: progress, published, rejected, or retracted. To upload a record, you just simply click on the button Upload a Record. There will be a form that you need to fill in with all the information related to your record. And once this is done, I'm going to show you the case indeed of a form already filled in with all the information. You can save the record or submit it for publication. In case you save the record, it will be saved as draft. You can edit it further later. You will see it clearly displayed on the screen that the record has been saved in a status of draft. You can then re-edit it, and or you can delete it if you still want. So if you edit it again, and in this case you want to finally submit it for publication, you can even write a message to the moderators in case you want to. We will ask you once you click on the submit button to confirm that you read the policies on Materials Cloud Archive. Once this is done, the record is in a status of review. The moderators have been informed of your submission and will review it and contact you. So if once the record is published, you can edit it again, in particular to change keywords and references, or if you want to create a new version of it. For keywords and references, you don't need to pass through a moderation phase, but it will be published automatically. For a new version, you will make the changes and submit it again. So if you want to search for a record, there is on the top menu an input field where you can insert, for example, part of the DOR, the entire DOI, or any word you would like to search for example, the name of the author. There is also keywords on the left that will help you to further filter through the results. In case of need, you can find help on the application in the frequently asked questions. We will try to keep this page updated regularly with all your questions. And of course, in case you have any question, you can contact us via email at archive@materialscloud.org. I'm concluding telling you that, reminding you that the Materials Cloud Archive is recommended by the Nature Journal Scientific Data, First Sharing, RE3 Data, and is also indexed by Google Data Search and B2Find. Thank you for your attention.
Thank you very much, Valeria, and thanks to all the speakers. So now we have time for a few questions. I will just pick a few of those we have already answered, but just to the benefit of everybody. We have already seen a few more we still didn't answer, or we'll answer all of them. We'll actually try also to collect them and then publish the answers, but you can already see the answers to the questions in the Q&A. Maybe I start with a first question for Sebastian. And the question is the following. So with respect to provenance and reproducibility, does AiiDA also store information about applications such as linked libraries, loaded modules, etc.? Sebastian.
So this particular information about the code specifically is not required, but when you configure a code into AiiDA, it will give you the opportunity to add this very information. So both to make it, to run it automatically. So if your code actually requires certain modules to be loaded before it's run, you can add all those lines and everything that's necessary before the binary is actually called on the supercomputer. And at the same time, this also functions as a sort of metadata such that it's stored in a database, so you can see after the fact exactly which modules have been loaded.
Thank you. A second question, probably also for Sebastian, is how does AiiDA gracefully handle failures, either recoverable failed calculations or pathological ones which don't converge?
So to answer this question, I want to stress again that AiiDA itself has been designed to be code and domain agnostic. So AiiDA itself cannot recover from any code-specific errors. So if we talk about PW, AiiDA doesn't know how to recover from convergence problems, but instead the plugins, so the AiiDA Quantum Espresso plugin, it implements this error handling. And so again, for this example, the AIDA Quantum Espresso plugin. We have the PW baseboard chain, has various error handlers to recover from out-of-wall time problems, for convergence problems, for all sorts of typical problems that you encounter when running PW. But I want to stress that this is the responsibility of the plugins. Luckily, we already have quite a few plugins for all the well-known codes such as Yambo, VAS, CP2K. You can find this list on the AIDA registry. I'm not sure if it's easy for us to share a link, and you can look in each of these plugins for the code that you might want to run to see what error handling they specifically support and provide.
Thank you. Now maybe a question for Sasha. The question is, should my institute be registered already to use the AiiDAlab?
Yeah, so basically we have a couple of instances running AiiDAlab, a couple of AiiDAlab servers, and we are currently preparing one that is open for the whole world, which will be deployed on European Open Science Cloud. So for that, you basically need to provide either your email address, or I mean, you can. The registration procedure is quite simple. So you can go with your GitHub account, Gmail account, or whatever you want. Also, I want to mention one thing, that AiiDAlab itself is open source. So if you want to deploy AiiDAlab on your machines, you can do that. And we have all the scripts like Ansible roles that will help you to that basically automate AiiDAlab setup. So you can, if you want to, if you're interested, you can just contact us and we'll help you with setting up AiiDAlab on your university resources.
Thank you, Sasha. Maybe another question for Sebastian, which is where is the data stored by AiiDA?
Can you specify, are you looking after the data that it's stored, whether it's in the file repository of the database or on which computer, on your local machine or the...
Maybe a combination of both questions, okay. I guess.
So I'll address the part that AIDA is typically installed on a researcher's laptop or workstation, even though it can also be installed on the supercluster itself. But typically it's installed on the user's own computer. And so the calculations will be run on the supercluster. And so the input files will be copied over. And once the calculation is done, both the raw inputs and the raw outputs are retrieved by AIDA and stored on the local machine. So on your local computer in the file repository. On top of this, the parsers will parse part of this raw output data and store them in the database directly in nodes, as these output nodes that you've seen in one of the provenance graphs that I've shown. The benefit of this is that once the data is in the database, you can actually query for it, which makes it possible to do very fast and efficient analyses of all the data that's in your database. So there's these two parts, the file repository and the database. Hope that answers that question.
Thank you. So maybe I would ask maybe a final question also to Sebastian, which is maybe you will find the links in the questions and answers, but maybe at least maybe interesting for everybody to listen, which is if I want to develop AIDA for some other code, so I guess it's here asking about AIDA plugins, who should I contact, or I can directly do it without obtaining any permission?
Well, first of all, you can do this without permission. If you want to write your own plugin, this is completely up to you. But before doing so, I would recommend you to go to the AIDA plugin registry. You will find a link in the questions that have been answered. This is a website online that is a registry of all the plugins that have already been developed and are available, such as AIDA Quantum Espresso for VAS, CP2K. And currently we have 50 registered packages. So the chances that there are for your materials science code that already exists are large. So before redoing the work, please have a look there. If you find that your code is not supported, you can, as I said, without permission, develop your own. And we actually recommend that you already register it at the registry. This is not required, but this might be useful if you are willing to collaborate with other people, but you can also keep this private. And to get help in developing this, there are tutorials on AIDA's website. And especially, there should be a link to the AIDA diff plugin package, which is essentially a cookie cutter. You can basically, with a simple command, you can really start the skeleton for your plugin and gives some easy steps to get going. And then there's a documentation for advanced information. And of course, you can subscribe to the AiiDA mailing list, for which you also will find a link in the answered questions, where you can ask questions to the community. This is typically low traffic, so you don't have to worry to get spammed, and there's relatively useful information. And both the core developers, such as myself, will respond there, but also other collaborators that are outside of the Max and the AiiDA project, but that have been using AiiDA for their own research will typically respond.
Okay, so thank you very much. I'll now move to the closing remarks. I will actually take the occasion also to answer one final question, which is, are there any workshops organized to learn how to work with AiiDA? The answer is yes. I already answered to similar questions. We'll find the answers. But if you go on the AIDA.net website, you will find the links on events and tutorials. And if you click on tutorials, you find virtual machines and the full documentation on how to run AiiDA. Is quite self-explanatory and very well detailed. And we will have another one which we'll advertise soon on the Max channels, on the Psyche, or in the mailing list, etc. This will be the second week of July. Then the information will be forwarded in the mailing list probably next week or in a week or so. Now, let me just conclude to thanking first of all the speakers of today. So Sebastian, Sasha, and Valeria. I want to thank also all the Max support team who helped us organize this, this webinar. And I want to remind you what you also see on the slide here, that the next one will be on June 16, and we'll focus on the Yambo code, and the speakers will be the developers on the Yambo code, which is one of the Max flagship codes. And then, of course, let me thank all of you for your participation and attendance. I want just to remind you that videos of today, the slides, and additional material will be available on the same Max event webpage from which you registered. And thank you very much, and see you soon.